how do you tell x is the best? So we have this and we have this unconstrained, constrained. How do you tell x is the best? So we have FOC, first order optimality condition. Okay, before FOC, let me talk about ZOC, zero order optimality condition. So x is minimizer if what? Fx star smaller than Fx for all x, right? Definition, right? Then this is zero order optimality condition. Basically, this is the definition of what is the best x. Here's the problem. This is useless. Why? Because if you want to check this, you have to check for all x. Impossible. Better one is to do FOC. This one is given by Fermat. The one Fermat last theorem. It says if gradient is 0, that's it. Important. Actually, it's not gradient. It's negative gradient. Okay. Do what the heck is this? In other words, Fx star smaller than Fx for all x. This is zero order condition. It will if and only if this. So in other words, you can go from here to prove this and from here to prove this. These are details. Not going to prove here. Then what? What happens if I have a set x? If I have a set x, this is false. Does not hold. Here's the idea. If you have a set x, this one becomes something else. And this is what I'm going to talk about. Okay? This is the idea. If you have a set x, can you say this? No. So what is this? Gradient f is 0. And then x star is in C. This is actually wrong. The correct one is gradient is in something. Looks like this. Oh my gosh, what is this? This is called normal cone. Normal cone, what does it mean? Normal means 90 degree to something. Cone is cone. Then we talk about what the heck is this. This is the expression. What the heck is this? Let's look at it one by one. So I have a set S, subset of Rn, and then I have a point small s. So normal cone to a set S define as this. If small s is not in set S, empty set. If small s is in set S, blah 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 blah. What the heck is this? First of all, this is a set. This is order V such that this is true. So this is not a point. This is a set, number one. If this is a set, then we can argue, is this set convex set? Is this set not convex set? Not yet. And if this small s is not in the big S, we have empty set. Empty set is always convex because nothing plus nothing is inside nothing. Okay. So therefore, we care about this. So we have two things, a set and a point. What is this? A set, the big X, and a point, the X star. So this is a set. So this is saying, if my gradient belongs to a set, then this is the optimality condition of this. Okay. So now explain what the heck is this. Let's look at this figure. One, I have a big S look like this funny shape. Okay. And my small s is this point. And my X is red. Okay, right? This big S is a convex set. Okay. Convex shape. Okay. Why? Because I have hyperplane, 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 hyperplane. This part is a circle, is a convex. Okay. Then what? Number two. This thing, this is 0. Okay. This is a vector on X. Okay. This is 0. So this thing is vector on S. Then what is this green arrow? This green arrow is X minus S. Why I need this green arrow? Because the expression have X minus S. So I have this green arrow. Okay. What is this thing? It's saying all the V such that inner product is less than 0. Inner product less than 0 means the angle is larger than 90 degrees. So that means this thing is order V. The angle between the yellow and the green have an angle larger than 90 degrees. This is 1V. This is order V. What does it look like? 90 degree to this point, right? Because let's zoom in. Is this 90 degree? Yes. Is this 90 degree? Yes. Then everything inside here is 90 degrees. It's because this is the most extreme point. This is the extreme ray. This is an extreme case. So everything inside here is at least 90 degree. Other than 90 can be 91, 92, 93, 94. We don't care. Okay. So this is the idea. So this is a cone. So what does that mean? This is called normal cone. So if I have a circle, this point, I zoom in. What's normal cone? This is the normal cone, 90 degree. And in this case, my normal cone is just a line. I cannot have a triangle because But what if my shape is like this? This is 90 degree. Then what's the idea? The idea is I have a green arrow here. I want any arrow in yellow 90 degree or above from this. So what's the 90 degree? Okay, it will be something like this. Okay, or what? Suppose I have this. Then at this point, 90 degree here. This one, something here. So this is called normal cone. You can think of it as normal to something. Then this thing is what? It's a cone. Now go back to the optimal condition. It means, is this point a solution? This point is a solution if what? If gradient, negative gradient is inside this cone, then this is a solution. That's the idea. Okay, I'm not going to explain. So what the heck is this? So these are the math of the normal cone. So if V is a vector inside this cone, what's the definition of cone? Any lambda V is in the cone. So let's talk about it. V is in a cone means this is true. This is definition. If I put lambda here, I just scale this. Lambda do not change this way. Lambda is larger than 0. So done. It's a convex set. V1 in cone and V2 in cone imply Yang-Sen's expression is in cone. Okay, blah 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 blah. It's just detail. It's true. Next. So now we have this thing. What the heck is this? If I have a set S and I have a point S, this is the full expression. If S is on the boundary, I have a cone. This is the cone. If S is here, then the cone is nothing. It's 0 vector. If S is here, the cone is empty set. So you can think of, if I have a point here, my cone is this. If I have a point here, my cone is this. If I have a point here, normal, right? A point is this. this thing will change the shape if I sliding along the blue line, and it will become a bigger set if it's on this corner point. If this corner point, okay, this is 90 degree, this is 90 degree, so this is the normal cone here. And then if it is here, then it's 90 degree, just a line. So basically, normal cone will have funny cone only in this corner point because they are 90 degree. But if you are in a plane, then you just have a straight line. And if this point suddenly go inside the set, becomes zero vector. And if this cone go outside the set, become empty set. So it's like this. So you have three cases: on the boundary, on the interior, or not in the set. Okay, in the boundary, you have this thing. Not going to prove it. This is definition. I just explained what the heck is it. Now we prove these two things. If this is inside the set, if this is inside the set, okay, that means we have blue. What's interior? Interior means you have set. I have a point here. That means you can always throw a ball. That the whole ball in the set, right? So there exists a ball. This whole ball is in the set S. Okay, and what is a ball? A ball is center a point and a radius. Center at S, radius delta. Okay, now I have V. V is a vector in this normal cone. Normal cone definition is this, right? So I have green. And now I have what? I have X in X is what? X is this guy. So by blue and red, now I consider this thing. What is this thing? S plus TV. S plus TV is S moving along T. Okay, no, along V, S amount. Okay, then I use green because of this. So S plus TV, this whole thing is the X. Then I have what? V inner product with this thing, which is this thing, because S and S cancel out. I have this thing, which gives me something smaller than 0, which is impossible. Therefore, you have to get 0 vector. This is true only if V is 0 vector. So therefore, you have 0 vector. Because T is positive distance removed. Okay, that's how easy proof. Okay, then this is convex analysis. What's the point here? Of course, it's useful here. What is this? If X is a solution of a constraint problem, now it's not gradient is 0 norm. Now it's gradient in normal cone. How to prove it? Here, assume X is a solution. And let's say this is false. This is not true. If this is not true, that means I have this, right? If this is not true, that means there exists a D that we can keep going on. But I just said that if you keep going on, you get 0 vector or you get empty set. So you can't. If you have a point that you can keep going on, first of all, you decrease the objective function value, then it's contradicted to this is me. Secondly, if you really move there, you will what? You will move from here, either go out or go in. You go out, empty set. Go in, 0 vector. You can't. So therefore, you can't do that. So therefore, this is always true. So this is now the funny thing. What is the funny thing? The funny thing is what? Let's go back to the problem. Mean f x larger than 0. What is this? This is x in C, right? If my solution is here, everything is positive. What's the optimality condition? The optimality condition is this is 0. Why? Because this point is in interior of my C. So optimality condition is this thing belong to normal cone. Normal cone in interior is 0 vector. So, but what if my point is here? If my point is here, y value is positive, but x value is just 0. Then it will say my gradient f negative inside normal cone, which is this line. So it means what? X coordinate is this thing, negative t for any t larger than 0. Y coordinate is somewhere here is 0. So it means if I have two-dimensional problem, then my negative gradient on x star, that means something, I call it a, b, will have the following form. A will be anything negative, or a is just some t larger than 0. What is b? B has to be 0. So this will be the solution. If you have a vector that give you this, that point is a solution. Okay. What about if I have a point here? Then this is the normal cone. Then you have 0, 0. But this is outside. This thing is empty set. So this point cannot be solution. Okay. Come on. This thing is outside the set. You don't have normal cone. It's empty set. Right? Then you have this thing belong to empty set area. So not solution. Okay. Then this is the idea. So if f is convex and differentiable, now I have no C. My C is the whole space. Then I have 0. Why? Because now if my C is whole space, this is always true. Because C is the whole space, you are not in boundary. You are always inside a set. So normal cone becomes 0 vector. And because this belong to 0 vector and 0 vector is singleton, then this thing become equal sign. This is why you have equal sign. So that's why you have optimality condition. Here's an important thing. Usually people will say that, oh, it's gradient equals 0. No, it's this thing equals 0. People skip this part, then they forget actually it's negative in normal cone. Okay, that means if you say this mathematically is correct, but that means you don't understand normal cone. It should be this. Okay, so how do you prove it? Okay, I just said that normal cone at interior point is singleton. Why? Because R is the whole space, so any point is always inside the interior. Done. Okay, this is summary. So you have this. Make sure you remember why there's a negative. The negative is because of this. But anyway, and then this is the general word for any C. You have this. The condition is this C cannot be empty set, of course. Come on. And then also your X star need to be inside. Otherwise, this gives you empty set. And you have these two cases, either this thing or this thing. This is in S, so this thing you can keep going on to two cases, is a BD and and int. And with your int, this whole thing reduced to 0, which is this point. And how do you get this thing? Is 3 imply 2 with this give you 1. So this is the optimality condition. So that means this is how you check when optimization problem converge, the algorithm converge. You just check this thing. For differentiable problem, you check this thing with no constraint. With constraint, you check this thing. So how do you check? You check this. For this thing, you just check this. Because this is how far you from 0. What about this thing? You check distance of this to normal cone. Now this is what? This is a lot of things you can write. You say, I want to find the distance between my negative gradient to a set. Then you need to know what's the expression of the set. And then you find the expression of gradient. Probably is just something, this thing, minus some thing for in this normal cone. Okay? Then this is a distance, right? Then you can do that. This is one way. But this is very complicated because this is an optimization problem. So nobody do this. But this is for theorem.